Okay, hello everyone, I'm Raphael, I'm from the University of Leicester in the UK, and I'm going to be talking about a somewhat novel method of solving level set shape optimization using aggregated polytopic meshes. So this is a scheme developed by my supervisor, Manolis. He's in Scotland now, I think, in the UK. So essentially what I'll do is I'll do a quick, brief recap of what level sets are. That should be fairly straightforward. Then I'll go on to talk about how to solve the level set equation using DG methods, that's Discontinuous Galerkin. And then I'll talk about the shape optimization of the level set equation, followed by some methods of solving. And then finally, I'll talk about some initial results that I have gotten recently. So, simple definition of a level set, it is the region of a function that is constant. If you think of it as a height map, say that any contour of equal height is a level set. So level sets tend to look different depending on the dimensionality of the problem. So in 1D, the level set is just a set of points. And in 2D, it's given by a line, in this case, a circle. It's also worth noting the parts that are positive and parts of the function that are positive and negative. So we have the super level set above and the sub-level set below. So for level set equation, what we want is to update the level set function, and we are interested in the interface between the level set function and the zero plane. So we have a velocity field that updates the level set function as it goes along, and we're interested in this interface. So in this situation, we have the function coming out of the zero plane, and it creates this splitting blob. So just some quick definitions here. So the level set here is defined as this partial gamma. The sub-level set is given by this gamma, and omega here is our Holdall domain. So the region gamma, which is the sub-level set here, and we are solving the level set equation, which is given here. So we have our temporal derivative, our spatial derivative, and our velocity function v here. And we want the velocity v function to be a shape gradient that arises from a shape function minimization problem. So how do we solve the level set function, or level set equation? So the original scheme developed by Sethian and Osher was to use finite difference methods. And so this here is quite a basic upwind method. But of course, finite difference methods suffer from lack of creativity with the domain geometry. So instead, we'd like to use continuous methods, finite element methods. So to formulate the level set equation as a finite element problem, we simply just multiply by test function and then integrate over the domain. Nothing new here. But the issue is that basic continuous finite element methods tend to perform quite badly on hyperbolic problems, specifically the level set equation. So on the right here, this is a very basic convergence of a continuous finite element method, and we can see that it oscillates as it attempts to converge, and will likely never converge to an acceptable solution. Whereas below, I have P1 and P2, so a polynomial degree 1 and 2, for the DG method, Discontinuous Galerkin. And we can see that DG methods work or can solve the problem much more effectively. So what's the difference between CG and DG? Well, as one might expect, DG is discontinuous. So there's no requirement in a DG method for elements to be congruous at the edge. So we can have massive leaps or discontinuities between elements. So how do we formulate the finite element, the level set equation as a DG scheme? So first of all, we set up our family of polynomials here, and we derive the weak form the same way as we would for the continuous method, just multiply by a test function and integrate over the domain. But we will note that this is not consistent. And the reason for that is because there is no communication between the elements. Effectively, the basis functions on a DG method are only locally defined, which will lead to possible shocks or oscillations. So what we need to do is we need to add this upwind term here. This upwind term is given by this formula. So in this formula, we have n, which is, oh, hang on. And this, just one thing, this term here is defined not on the element, but on the element edges. So here in this formula, we have n, and n is the normal vector to the edge, and we have these phi plus and phi minus. And what this is this defines the inflow and the outflow edge of an element. So if we have our element edge here, and we have the velocity v passing through it, we have our outflow edge, which is the plus side, and the inflow edge, which is the negative side here. And down here, this is the full expansion of this term. And we'll see that at the edge of the Holdall domain, we have G here, which is our boundary condition. So that's how to deal with the derivative, the spatial part. Now to talk about the temporal part, we simply time-step the problem using a Runge-Kutta method. Now, I'm sure everyone knows what a Runge-Kutta method is, so I'm not going to explain this. But yeah, that's how we time-step the problem. So now I'll talk about the level set optimization. So what we've been doing so far is we've been using this test case of our shape function equaling some arbitrary real-valued function. And we said that the level set method computes the solution to this minimization problem. That is, the function f here, or the solution to the level set equation, or level set optimization, is the set here, which is the level set of function f. So what we can say is that f is a target function. So we start off with our level set initial condition, and then we optimize to this target function. And so by defining a vector field, V, or W even, we have this Eulerian derivative, and we get this operator, this shape derivative here. So this is the standard solution to a real-valued function. And so what we want to use is the shape gradient, v, also known as the velocity function, to perform steepest descent method to optimize our problem. And so this here becomes this with the elliptic operator here. And then we can solve this using continuous Galerkin methods. So two things of note is that we use H1 here because we want homogeneous Dirichlet boundary conditions, as this will prevent the level set from leaving the Holdahl domain. And we note that the velocity function v has to be continuous, otherwise it can lead to shocks and oscillations. So what we end up with is effectively this coupled system, which is made up of the level set equation and the velocity equation here. And information needs to transfer between one and the other. So we need to transfer the position of the level set between the first equation and the second one, and we need to transfer the velocity from the bottom to the top. And the main difficulty with solving this system is identifying the level set or the sub-level set. So the first method that we came up with was an sort of a naive approach of adaptive quadrature. So if we have our base mesh here, and we start with our initial level set here, which is just simply x squared plus y squared minus 0.4, we have the circle of radius 0.4. And what we do is when we reach an element that is bisected by the level set, we split the quadrature. So instead of performing quadrature over the entire element, we now have a split quadrature between the area within the level set and the area outside the level set. So as an experiment, we have on our initial condition, we have this initial condition here, and we have a target function, which is this fourth degree polynomial. It's not too important, but this is our initial condition. So the black line here is our level set function, and the purple dotted lines here are the target. So we time step this, and we get some kind of optimization like this. Not particularly neat, but there was one big problem with this method, with the adaptive quadrature method. And that was, and it's more easy to see on a 1D method. So this is a 1D level set here. We have the black line here, which is our level set function, blue line here, which is our target function, and this orange line is the velocity that we have. And what we note is that at the points where at the level set exactly, we'll note that these points here are not continuous. And this is a problem because if we have an element crossing this, crossing the level set like this, we won't get an accurate solution. It won't be able to resolve the region near the level set because the basis functions are smooth. So what we need is for the edge of the elements to exist at the level set. So therefore, it is advantageous to locally refine the original base mesh so that the level set lies on the set of edges of the mesh. So to locally refine, what we do is when we find an element that is bisected by the level set, we first interpolate the zeros along the edge, and then we split the element into 3. Simple enough design. And so what we end up having is a mesh that would look a bit like this. So wherever the level set exists, we've split the element into 3. And what's quite good about doing things this way is that it only requires manipulation of the elements that lie on the level set. The rest of the mesh remains unchanged, so we don't need to regenerate the mesh at every time step. One problem, though, is that as the level set gets close to a node, we'll get this kind of degenerate elements that form. And the degenerate elements like this are not well defined on a continuous basis. So what we require is a way to preserve this boundary here whilst avoiding the formation of degenerate elements. So I present the method of polytopic aggregation. So what we do is when we have our base mesh, we initialize a base mesh or a fine mesh made up of conventional elements, let's say triangles, for instance. And then we define a set of centroids, which are these colorful dots here. And what we do is we aggregate all the elements near the centroids together, kind of a k-means approach. One thing to note, though, is that we cannot solve this using continuous Galerkin, since the mesh is non-conformal. You can see that we have quite a few hanging nodes in places. So to solve it, we need to use a DG method instead. So if we have a mesh like such, we define 2 sets of centroids, the centroids within the level set and the centroids outside the level set. And we agglomerate them separately. And what we end up with is the region of the sublevel set and the region outside, or the superlevel set here. So how do we define the basis functions on a strange polytopic element? So the way to do this is that we create a bounding box around the element, a tight-fitting bounding box, and we define the tensor product, the Legendre polynomials, across. And then how do we perform quadrature over the element? Well, this is still in progress, and this method is currently still quite slow, but it is to basically split the element up into its microelements and then perform quadrature over each of them individually, a subtessellation method. So to automate the polytopic meshes, we use a k-means approach. So we set up our base mesh, and then we set a bunch of centroids randomly placed throughout the mesh. And then they sort of just diffuse across the domain to create kind of equally sized elements, roughly. That's one method. And the other method is a weighted k-means, where basically the level set acts as an attractor. And so the centroids will be pulled closer towards them. And so we get more elements closer to the edge or to the level set. So, as I said, we cannot use continuous methods to solve a polytopic method like this, so we use the DG method. The way we do this is, so Buffer and Ortner stated that the way to do this is to basically replace all the derivative terms with a lifting operator. So I've not included the derivation here, but if you want to see it, let me know. And basically, we end up adding these 3 extra terms here, which produces a family of methods called the interior penalty DG methods. So we have these square brackets here, and we have these curly brackets here. The square brackets define the jump between elements. So we have our jump term, and then we have the curly bracket, which define the average term. So that's sort of mid between the two extremes. You'll also notice that we have this term here, this sigma. Sigma here is the penalty constant, and it defines to what extent the discontinuity between the elements is penalized. So if sigma is huge, it'll try and penalize the discontinuity as much as possible. Whereas if it's quite small, it'll give it a lot of freedom. But in giving it a lot of freedom, we can get some sharp jumps and shocks. I think sigma is equal to like the degree of the polynomial squared divided by the element size, I think. So I'll perform the same experiment again here. And yeah, so this is the same experiment as before with the adaptive quadrature method. And so we end up with a mesh something like this. So this here is our velocity function, and this is the same thing on a heat map. And so we have the areas, the blue areas here, which are negative velocity. And we have the positive areas here, which are the yellow areas, which are positive velocity. And so if we time step this, we get a similar kind of result in here. But the issue that we have now is you'll see that we have this bit here, which sticks out a little bit. And the reason for this, I think, is because we need to refine the elements closer to this edge here. This is the same thing, but with the y component of the velocity. And so you can see that it attempts to like sort of close the gap between on the blob, I guess. Yeah. So yeah, so this is basically to show that it currently is working to some degree. So basically, to conclude, I have introduced a fully DG scheme for shape optimization on polytopic meshes. I'd say the main pros of this method is that we can isolate the sub-level set much more easily using fewer elements. In fact, we could probably use fewer elements, but higher P, higher polynomial degree. And the other positive is that because of the way we perform the local refinement, the mesh does not need to be regenerated after each time step. The cons, I'd say, I didn't go through this, but if a polytopic element is too crazy, let's say, like very like concaved, then the method requires an extra step in order to solve accurately. And the other problem currently is that given the method that we use for subtessellation is currently no faster to perform quadrature on the polytopic elements than it is on a regular simplex. Cool. And then for future work, hopefully we can apply this to a PDE constraint problem, perform some error analysis, quite importantly, to try and perform adaptive mesh refinement or coarsening, try and find the optimal way to position the centroids on the mesh. And then if that all goes to plan, maybe we can use some GPU matrix assembly for even faster optimization. Yeah, so thank you very much. I just want to acknowledge my supervisors, and UKRI, who's funding my project, and the University of Leicester, and of course, ESI for inviting me. Thank you very much.